Okay, well, so today we're going to talk about invariant subspaces of L2 mu, and here we have just some notation wise to set up. We're specifically talking about L2 space with respect to the measure mu on the one-dimensional torus in the complex plane. Okay, so that is just, I'm just going to write the set here so there's no confusion. I'm sorry my T looks like a pi. I might just write regular T from now on without doing the blackboard. That's all the set, all the unimodular complex numbers. Okay, and here mu we're just assuming to be finite and non-negative as a measure. So mu finite and non-negative. Because a lot of this theory, we have complex measures and signed measures. So it's important to make that distinguishment. Okay. Things will change depending on what we want our measure to look like. All right. And then what we're also going to be dealing with is m, so the Lebesgue measure, but this is going to be a version of the Lebesgue measure. So m here, I'll put this in green, m, we'll just say that the Lebesgue measure on the torus T, so I'm just going to use capital T. Is that not a really good idea? We'll just use T and see how that goes. So this is normalized. And what I mean by that, I'm just gonna define the measure this way. So I'm going to say that the measure of the set, so if I take an arc of the circle, so e to the I theta, where theta is bounded by two angles, so theta 1 is less than or equal to theta is less than or equal to theta 2. Okay, that is just going to be equal to theta 2 minus theta 1 over 2 pi. Okay, so one thing you notice immediately about this measure, it's a probability measure. Okay, well, why is that? Well, because if I take the measure of the unit circle, I get 2 pi minus 0 over 2 pi, that's 1. So this measure tells you what percentage a given arc covers the unit circle. Okay, so if you write everything in terms of, pi, okay, you're going to get a percentage. Okay, so this tells you how much of the unit circle is covered by an arc. Okay, so let me just do an example. And I'll do an example here because we're not all coming here with a boatload of measure theory. So if I have the unit circle here, that's as good as it's going to get. And I just say half of it, I'm just considering the measure of this green arc. That's going to be the measure of that, the Lebesgue measure of that. And we're talking about on T, we'll just say that arc is gamma. Well, that's just going to be 1/2. Or you could say 50%. No one says that. No one says 50%. So it's up to you whether you want to do that. Okay. So hopefully no questions on that, but if you do, please let me know. But this is what we're going to be working with notation-wise. And then the space we're going to study is L2. Okay, so this is called Hilbert space. It's the one you work in physics. Okay, but we're specifically going to be talking about functions whose inputs come from the torus. I shouldn't say torus, the unit circle, and output anywhere to C. So we're talking about functions on the unit circle, not disk. Okay, this is very important because this is a setting for harmonic analysis. So I'm going to just call it L2 mu is the shorthand, but formally you can say L2 mu T. And that's just going to be the set of all f measurable. Okay, these are complex valued functions whose inputs are on the torus or unit circle, okay, that are square integrable. So the norm of f, the 2 norm of f squared, okay, so this is the exponent here. This isn't superscript notation. This is a exponent here, right? This just so we can remove the square root. The integral, okay, it's just square integrable. So its integral over the torus with respect to mu is less than infinity. And this is really easy to compute, right? Okay, so this isn't something too abstract, because when you take the integral over the torus, okay, you can write things in polar coordinates. Okay, if we're just forgetting, we're like, okay, this is the normal integration that you do in high school. Okay, this will just be the integral from 0 to 2 pi in nice cases, if you want to think about it like that. Okay, so we're going to be working in L2, okay, and then so this is a Hilbert space, and you may be familiar with the inner product. We're going to be working with that today, but the inner product here is just your standard one. So if I have two functions, so these are in L2, okay, the inner product is going to be the integral over the torus of f times the conjugate of g, the complex conjugate of g, d mu. Okay. So we have this Hilbert space that we're going to study today, and specifically we're going to be studying some closed subspaces of this. So in this talk today, we're going to be assuming that anytime I bring up a subspace, it's closed. Okay. Now I don't think too many of us have had functional analysis, so that's okay. This is going to be closed with respect to functional analysis. So I'll bring you up on some things like orthogonal projection if you're not too comfortable with that. Okay, but closure in the sense, we have a norm here, we have a metric. So you have the usual notion of sequences and convergence and closure and stuff. Okay, so this isn't anything super abstract at the moment. Okay, all right. So specifically we're talking about subspaces. Okay. And a particularly closed of L2 mu, or to say an L2 mu or whatever. Okay, and the ones that are interesting for us are those that are invariant. And an invariant has a really simple. So there's types of invariants. The easiest type and the strongest of the two is double invariance. Okay, and the other one is singularly invariant. Okay, but in general, invariant means just if I don't say anything else, there's no adjective. Invariant, so E subset L2 mu, that's going to be called invariant if I multiply every element of E by Z, I'm still within the set. So Z, E, and I write that as shorthand, is a subset of E. If those are equal, so if Z, E is equal to E, this is called two invariants or doubly invariant. Okay, I'll just say doubly invariant. Okay, and what does that mean? Multiplication. Now remember, E, what are the elements of E? Functions. Okay, keep that in mind. All these subspaces are subspaces of functions, so we're going to be working with that today. Okay, so it's invariant if just in general we have this inclusion, but it'll be doubly invariant if ZE is equal, if we have this equality. And this is equivalent to another condition I'll talk into a second. But when it's the case that this inclusion is proper, okay, so I'm going to call this, we'll just call this 1. So if 1 is a proper inclusion, this is called, let me make sure I get this is called singular. Oh no, simply invariant, not singular invariant, simply invariant. Or you can say one invariant, which is why I was calling it singular invariant. And there's singular operators being discussed. But anyway, so it's simply invariant if ZE is a proper subset of E, and then it's doubly invariant if ZE is equal to E. But in general, if ZE is just a subset of E, we don't know anything else, you would just say invariant. Okay. Now this is motivated when we talk about multiplication operators, so kind of getting more comfortable with this and how this relates to Hilbert space and how this interacts. You can actually restate, is it subset? So, well, you can just say subset, but I can, they could be equal. So invariant, I don't know, they could be equal as sets. That's a good question. So Nikolai asks, is it subset or subset equal? So they could be equal, but just if I just say invariant, it's subset. There's not necessarily proper or not. Okay, but if it is known to be proper, then you would say it's simply invariant. Okay, there's another way of, and I really want to discuss this because this is very important. This was actually von Neumann's idea, okay, of characterizing this kind of invariance. And I think it, if you're more familiar with operator theory, this can be more, maybe a better way to think about it. Okay, so von, I always get his last name wrong, Neumann. Von Neumann's, what would you say, approach? Or way of looking at it, we can just say. Okay, so I'm going to do this definition, and it's going to be about reducing subspaces. Okay, so given an operator, so T H to H. So this is just a linear operator. okay, on a given Hilbert space. Okay. It's reducing if we just have two inclusions. Okay. If I apply T to E, the image of E under T is a subset of E, and the image of the adjoint. Okay, well, what's the adjoint? We'll talk about in a second. We'll just talk about it very loosely. The adjoint of T applied to E is a subset of E. Okay. So that is so it's reducing if it's invariant under T and it's a joint. Okay. I mean, sorry. Yeah, it's reducing if it's invariant under T and it's a joint. So we can actually restate reducing subspaces. And I'm sorry. So this is from von Neumann, but this specific way of looking at doubly invariant subspaces is given by Wormer. This is from E is. Yeah, reducing. You're right. Yes, E is reducing. So E is reducing with respect to T. Yeah. Right. So E is reducing for T. Okay. Sorry, I just like to write fast. But so we have these two things. So you can actually to talk about doubly invariance, we can restate things in terms of the multiplication operator. This is something in composition operators and just in general operator theory that's a very interesting operator to study. It's interesting to study when it's a contraction. On what spaces of functions is it a contraction, meaning the norm of that operator is less than or equal to 1, rather that the norm of the operator applied to a function is less than or equal to the norm of the input function. Okay, so it's not just a fool's errand or sort of just being complicated for the sake to be talking about things in terms of the multiplication operator. Okay, so what do I mean by the multiplication operator? Well, the multiplication operator, I'm just going to call S mu. This is standard. I know we were talking about a measure mu, but this mu here is just for multiplication. Okay, that just sends a function f to z times f. Okay, so you're taking the product of the identity and the function. Multiplication. Okay. So you can restate things in terms of this. You can maybe think about it for a second. When we were talking earlier about this equality here, you can also say that this is equivalent to having ZE as a subset of E and having Z bar E as a subset of E. This is the same thing. Now, why is that case? Well, when you're on the complex unit circle, the conjugate of Z is equal to what? 1 over Z. So these two conditions are equivalent. Okay. Very easy to see. Okay. So if ZE is subset of E, because if Z bar E is a subset of E, right, that's 1 over Z E is a subset of E. You can see how you would get equality. Okay. So, thinking about it like that, okay, so this, you can look at this is our multiplication operator S mu. Okay, and then what's the adjoint of S mu? Okay, what do I mean by adjoint? I'll just give you a very simple definition. We're talking about the inner product here, right? FG, we're just going to, FG in our space L2. Okay, if I have some operator T, the adjoint satisfies this relation. So T applied to F and G is going to be equal to F and then the adjoint of T applied to G. Okay, so maybe you can guess if we have the multiplication by Z operator what the adjoint is going to be. And the adjoint is going to be exactly multiplication by the conjugate of Z. And we can do that just to check it, just for pacing. We can check that. So if I, claim the adjoint of S mu is multiplication by Z bar. Okay, easy exercise actually. Okay, well let's check that. So if I do, we'll just say S mu F, G, I apologize for that handwriting. S mu F, so that's going to be F times Z, well maybe I'll just do ZF. ZF times G bar, D mu. Okay, well I can rewrite that as TF. You can probably already see where I'm going with this. Right, conjugate of the conjugate. right there. You just move the z under the conjugate and take its conjugate. When you take the conjugate of that product, right, they cancel out, you get z. And well, that's exactly, and I'm omitting the d mu, but it's there. And that is exactly f conjugate s adjoint mu. Well, that's the claim. I'll just say, well, that just happens to be f s mu g. Okay, so it's the adjoint. It's multiplication by z conjugate. Okay, so now that we know what the adjoint is, okay, so what we can do is we can restate double invariance in terms of this by saying it's doubly invariant. From this, you can say that a subspace is going to be closed. Closed subspace will be doubly invariant if and only if that subspace is reducing with respect to the multiplication operator. Because what does that mean to be reducing? That would mean multiplication by z is a subset of E, and multiplication by z conjugate is a subset of E. Very simple way of putting things in terms of operators, but nevertheless very important if you want to work with composition operators and multiplication operators on spaces of complex valued functions. Okay. So a main question now, so we know what double invariance is, so a natural thing to ask is when is a subspace doubly invariant? So that's the question. We'll move over here. So question. When is a subspace, and I'll just say, that's subspace of L2 mu to invariant. How can we characterize doubly invariant subspaces? It actually turns out to be quite a simple way of characterizing them. And this is a result out by Norbert Wiener, or whatever. Yeah, Norbert Wiener. So he said all you need to do is find a characteristic function. And it's I before E except after C. Okay, there we go. Okay. So we're going to say let E be any closed subspace of L2 mu. Okay, again, I'm not writing closed subspace. We're assuming everything we're working with is closed. Then we're going to say that E is doubly invariant, which we can compactly write this way, if and only if we can find a characteristic function over a measurable set that when that characteristic function is applied to L2, we get E. Okay, let me say that again. E is going to be doubly invariant if there is a unique measurable set such that the characteristic function, the image of the characteristic function of that set as it acts on L2 is precisely E. Okay, so if and only if there exists a unique measurable, and we're going to call this sigma, which is obviously going to be a subset of the unit circle, such that I can say that E is equal to the characteristic function of sigma, characteristic function of sigma applied to L2 mu. Okay, now what is that? Let me write, you're like, okay, what's that characteristic function? That is the set of F. We define this to be the set of F and L2 mu, such that F is equal to 0, mu almost everywhere on T. That's what I mean by the characteristic function on T minus sigma. Excuse me. Okay, that's what I mean by the characteristic function. So if I can replace that with any set, but in this case, this is what the characteristic function means. It's a set of functions that are 0 on the complement. Okay. So we have this. This is actually quite simple for characterization of double invariance. Okay, we need to find a unique measurable subset such that E is equal to the characteristic function of that set applied to L2. Okay, and the proof is not too bad, so we're gonna go ahead and walk through it since we're talking about this anyway. So let's go over the proof. Let me pull up my notes. Okie dokie. So, all right. So let's prove the direct condition. Yep, for all So z here, that's a very good question. Z is any complex number. So z here is multiplication. So z here, you're talking about the multiplication. It's not by a point z, it's by the identity function. So because e is a set of functions, so if you had, let's say z squared is in e, then ze, you're going to get z cubed. And actually, before we dive into the proof, I do want to talk about this a little bit more. Maybe I do want to get a little bit more comfortable with this, because this example is going to come up. No, I'm glad you asked that question, because it reminded me I do want to show an example. Okay, let's just do a simple one. So if I have f and lu, so we'll just say sidetrack. For any f in L mu, and this is an important example actually, I'm really happy you brought it up. I want to talk about this set, EF, E sub f, which I define to be the span, just the linear span as you're used to from linear algebra, of this, and it's greater than or equal to 0, okay? Well, if f is the constant function 1, this is the space of trigonometric polynomials. Okay. So this is a great example of an invariant subspace. It's easy to check if it's closed. Okay. But this is invariant. Okay. So if I, and you can, and this is something that's easy to check as an exercise, but just as a solid example of an invariant subspace, this would be 1. Okay. So, trigonometric polynomials is 1, right? If I multiply an element here by z, right, of course this is going to be some finite linear combination. Okay, all of these are finite linear combinations, by the way. Finite linear span, I should be saying. So if I multiply this by z, I'm going to get z to the n plus 1. Obviously, that's in the space. Right, this is invariant. What is of interest, why this is interesting, and this will be the end of the sidetrack, is we want to know when functions satisfy this notion called cyclicity. And it's cyclic, so f is cyclic, we say. I'm not going to talk about it this time, but maybe next time. F is cyclic if this actually generates the whole space L2 mu. Okay, so something interesting, but anyway, that was the sidetrack. But let's get back to the proof. So to start off the proof, we're going to do the direct condition. We're going to assume, well, let me see. Which one do we do? We're going to actually do the converse first. Okay. All right, there we go. That's enough. So proof, we're going to start with the converse condition. Okay, so we're going to assume that we have this unique measurable set such that we have this representation as a characteristic function. Okay, so I'm going to say let E equal chi sigma L2 mu. This is easy. I need to now prove that this is doubly invariant. Okay. Okay, look at the representation of the set. Okay, let's start with, is it true that ZE is a subset of E? Okay. So if I pick out an element of this set, F is going to be 0 almost everywhere on T minus sigma. Okay. If I just do ZF, obviously then ZF is going to be, the point-wise multiplication. So if F is in E, then F, we're just going to say is equal to 0, and that obviously means almost everywhere. Okay, and that obviously will give us that Z times F is equal to 0 almost everywhere. So that's easy. And the same thing holds for the conjugate condition. So if I take conjugate of E, that is obviously going to be a subset of E. So we get double invariant just by virtue of this representation using a characteristic function. Right? Really easy implication to be proven here. Okay. The converse is a lot more complicated. Okay, so let's talk about the converse. Okay, so we've proved that if we can represent E as the characteristic function over a measurable set applied to L2, then it's doubly invariant. Now we're going to start off, okay, assuming Z is doubly invariant, assuming E is doubly invariant, can we go the other direction? The answer is yes, but it is a little complicated, but I want to go through it. Okay, the first thing we're going to talk about, so proof. We're going to start with steps. So step 1, we're going to let PE be the orthogonal projection of L2 onto E, of L2 mu. And you're like, what is an orthogonal projection? Well, let me just give you a really simple definition. Okay. So, if I have so E is a closed subspace. If I have a closed subspace of a Hilbert space, then always, this is actually a theorem, and so orthogonal projection is a theorem. Given any point in the Hilbert space, there is a unique point in the closed subspace such that the difference of those 2 points is orthogonal with every point in E. Okay, that's the general definition. Let me state it more formally. Okay, so if I have E as a subset of E of my Hilbert space H, we'll just say L2 mu. Okay, the set E perp, or the orthogonal complement, is the set of all F in L2, such that the inner product of F with G is equal to 0 for all G in E. Okay, right, you can see how this, right, 2 vectors are orthogonal if their inner product is 0. This is the generalization of that. Okay, so that's what I mean by orthogonal complement. Now the orthogonal projection, okay, is going to be made up of these points. So, right, okay, so, 1 second. Yeah, okay. So now, if I have F in E, and I'm sorry, F in L2 mu, by a theorem in functional analysis, there exists a unique G in E such that G minus F is in the orthogonal complement of E. And this G is called the orthogonal projection of X, little x. I'm sorry, the orthogonal projection of F onto E. Okay. So our orthogonal projection of L2 mu onto E is made up of these points. So G right here is going to be, right, that's what I mean by talking about the orthogonal projection. All right. So we're going to let PE be the orthogonal projection of L2 mu onto E. Okay. And now what I want to do is, let me make sure, wait, do I state this correctly? I just want to make sure. Yeah, okay, so PE, I'm going to say that PE is going to talk about taking a function f to its orthogonal projection, PEG. Okay. And this is a generalization of something from, as Abdul's posting from linear algebra. Okay, there we go. So this is, hopefully, I hope I don't want to lose anyone yet, because we're going to use this through the whole proof. So if anyone has any confusion about this, and by PEG, I mean this right here. All right, because I'm going to write the orthogonal projection of the identity map. And that is that unique element of the closed subspace, such that this difference is in the orthogonal complement. Okay. Yeah, so this is abusive notation. Actually, that's just, well, it is what it is. But do we have any questions on the orthogonal projection? Because this is a important part of the proof. Does anyone sort of understand the concept? Let me erase this, make this cleaner. Okay. Mm-hmm. So tropia is this just the statement that L2 is the direct sum of E with its orthogonal complement. Yeah. But we need this notion of orthogonal projection. Okay. So this is a very basic theorem in functional analysis. So yeah, that's a good way of stating it. Okay. So we have this notion of orthogonal projection. The second step is we're going to take the orthogonal projection of the identity map. So we're going to set chi, this is suggestive, is equal to the orthogonal projection of the identity map. Okay. Orthogonal projection of the identity map. And then one thing that you can check, is it true that 1 minus chi is an element of the orthogonal complement of E? This is a good way to see if you understand this definition of orthogonal projection. Well, yes. This is exactly the definition of orthogonal complement. I'm sorry, orthogonal projection of 1. So this is exactly the definition of orthogonal projection, right? If chi is equal to the orthogonal projection of 1, then 1 minus chi is going to be an element of the orthogonal complement. Okay, so that's easy. This is just by definition. Okay. Since E is going to be doubly invariant, so we know that E is, I'm going to abbreviate that to invariant. We know that E is 2 invariant. And we also know that chi is in E. Why? Because 1 minus chi is in the complement. Again, definition of orthogonal projection. Let me write that a little bit better. Chi is in E. Okay. And chi is in E. We're also going to get, by that, this is where we apply double invariance, that 1 minus chi is perpendicular to, orthogonal to, Zn times chi. Why? Because since E is doubly invariant, this is in E, the right-hand side. And we know that 1 minus chi is in the orthogonal complement of E. So it's orthogonal to everything in E. Okay. Okay. Because of this, we know that for any trigonometric polynomial, which we talked about earlier, we have that the integral over t of that of any trig polynomial p times chi times, this is just the inner product, right? 1 minus chi bar d mu. Well, that's just going to be equal to 0 for any trig polynomial p. All right, so that's going to be 0. The result of this is something very nice. What do we know about trigonometric polynomials and continuous functions? Well, if you remember way back to your days in analysis, this is the Arzela-Ascoli theorem, a result of it actually, excuse me. Any continuous function can be approximated by polynomials, i.e., the space of trigonometric polynomials is dense in the space of continuous functions over t. Okay. So let's say Arzela, and this is actually a very easy exercise to do. Space of trig polynomials, I'll just call that Paul, is dense. We can just write the closure, actually. The closure of the space of trigonometric polynomials is equal to the space of continuous functions on the torus. Okay. Well, what do we have here? And so there's actually, the next step here talks about, involves the Radon-Nikodym theorem, which is rather complicated. Oh, this is Stone-Weierstrass. Okay, there you go. Stone. Well, there's something about an algebra being dense in another algebra. That's right. There we go. Weierstrass. Thank you. Very good. Yeah, okay, so this is not Arzela-Ascoli. This is Stone-Weierstrass. There we go. Thank you. So the closure of the polynomials is the space of continuous functions. The next step involves the Radon-Nikodym theorem, so I won't go that deep because I don't want to lose you. But just think about this intuitively. Okay, so this integral is going to be 0 on a dense set. Okay, so you can think about, well, this is well-behaved. This is a you can say well-behaved integral. If it's 0 on a dense set, then if I add its closure, then it's not going to change. That's a very loose way of saying things. Okay. What I mean to say is the integrand here, the hidden step, but I won't go into it. So this defines a finite complex Borel measure. Okay, and the result of this fact here being 0 on this dense set is particularly that chi times 1 minus chi bar is equal to 0 almost everywhere with respect to mu. So this is equal to 0 almost everywhere. So that's the result. That's the result we get from this. Because this is equal to 0 for any trig polynomial, which follows by that double invariance, we're going to get that this integrand here is 0 almost everywhere with respect to mu. And all we do right here is simple algebra. So I'm going to write things out. I'm going to solve. So this is equivalent to this condition. So chi is equal to its modulus squared, mu almost everywhere. Okay. Mu almost everywhere. Okay, well then what is chi? Well, okay, when x is equal to the absolute value of itself squared, what's the locus of that? You can only have two numbers, 0 and 1. No other number will satisfy this equality. So chi is 0 or 1. What is chi? It's a characteristic function. There you go. Boom. So the conclusion is chi is equal to 0 or chi is equal to 1. The chi can only take on two values, 0 and 1. Okay. So I'm going to say sigma. I'm going to set sigma equal to this set t such that chi of t is equal to 1. Okay. And our candidate is chi sigma, which is just chi. Boom. So now we have to all we have to do is show that this is going to be measurable and satisfies the desired property, which is that E is equal to the characteristic function of chi applied to L2. Okay. So, because chi sigma is an element of E, okay, chi, right, this is the new notation I'm going to use. I'm just going to refer to chi as chi sigma. Right, we know, so I can just go ahead and say step 3. We know that chi sigma is an element of E. Great. Okay. And we have that the closure of chi applied to, what did I do for the space? Chi applied to the space of polynomials, that's going to be a subset of E. Okay. Now the closure of the polynomials is L2 equal to L2 mu. The closure of the polynomials is going to be equal to L2 mu. We're going to get that chi sigma of L2 mu is going to be a subset of, chi sigma, so we get the subset inclusion already here. So that's the first inclusion that we have. We need to get the reverse inclusion. To do that, what we can do is we can just verify that the orthogonal complement of chi applied to L2 is 0. Okay. So we're going to take, so what I mean by that, so we're going to so for the reverse inclusion is equivalent to verify that this orthogonal complement in E, so this is with respect to E. I don't know how you can orthogonal complement with respect to E is equal to this. All right, that's another way you can verify it. Common trick. Okay, so we're going to let F be an E, and we're going to say that F is perpendicular, orthogonal to the characteristic function applied to z to the n for some integer n. Okay, because E is reducing, right? We talked about this idea of reducing earlier, so this is going to come into play. Since E is reducing, we also get that we know that zn to the f is an element of E. Right, we talked about that earlier. Okay, and therefore, because zn to the f is an E, right, this is just a fact from earlier, we know that 1 minus chi sigma is orthogonal to zn f. Okay. And that's just by the construction of chi, right? We actually used this property earlier. Okay. So these orthogonality relations one thing that's cool about them, and I'll just finish off with this fun fact, you can actually rewrite these in terms of integrals. Okay, so the first one, right, we have that t, the integral over t of z n f chi sigma d mu. We have that is equal to 0. And that's for any n, by the way. That's important, because what we're going to get is the same thing we got earlier, right? 0 on this dense set, right? I can substitute in here any trigonometric polynomial, right, and just distribute it for through linearity. So we have these two facts by what's up here, okay? And so we get that x sigma f is equal to 0 mu almost everywhere. That's not, well, that's all right. And f times 1 minus x sigma is equal to 0. Same thing. Okay. So we get, because of this fact, we actually get that f is equal to 0 mu almost everywhere. Okay. So if f is in the orthogonal complement, it's necessarily the orthogonal complement with respect to E, it's 0. So the orthogonal complement, there's no, so the orthogonal complement of E is just going to be null. So in fact, x chi L2 mu is the whole space E. So we get the reverse inclusion, which is what we were trying to get up here. So we get the other way around. And that completes the proof. So now we have a full characterization of doubly invariant subspaces of Hilbert space on the unit circle. Okay. Now the question is, okay, and that's actually a very short story, right? This all fits on about half a page. The long story is when we talk about simply invariant subspaces. Okay, so we know that ZE is properly contained in E. And this is where the theory gets quite deep. You consider specific cases and then general cases. I have to maybe make a determination on what we should do. Let me see. But there are some nice properties of invariant spaces. So I'm not really going to talk about today because time will not permit the theory of simply invariant spaces. But it will be interesting to talk about an important class of functions, which is the Hardy class, specifically H2. Okay, and what is H2? So now we're going to go over to simple invariance for just a second. This is the last thing I want to talk about today. So now we can talk about simple invariance. Okay, so that is ZE is properly contained in E. Okay. And when you have this, when you have simple invariance, you actually have some interesting interplay with Hardy functions, and you're going to get this idea. This is where this idea of inner and outer functions kind of come from. Okay. You may have heard of these notions. Okay. And this H2, okay, so this is going to be a subspace, again, of L2T. Okay. And here, this measure that we're going to be working with is the Lebesgue measure. So this is just going to be L2M, or M comma T. So Hardy space here, what is Hardy space? That's just going to be F and L2 and L2T, such that if I write F as its power series expansion is equal to 0 infinity, right? Okay. Because if F is holomorphic, we can do this. If F is holomorphic, we can do this. We can write its power series expansion. Okay. This is specifically, and this should actually be negative infinity. Excuse me. Negative infinity. If it's actually particular that the expansion of F is not a Laurent series, it's just a normal Taylor series or Maclaurin series. Okay, so Fn is equal to 0 for all n less than 0. that's H2. There are some equivalent characterizations of H2 that you can see in other textbooks, such as the one by Joel Shapiro. It's a very good textbook. But yeah, there's a space of Hardy functions. So why do we care about Hardy functions? That's a good question. We care about Hardy functions because that is the natural analog of L2 in the complex plane. We want to talk, and just in general, actually. So we don't have to restrict our functions to the unit circle, right? We can take them on the unit disk, open unit disk, talk about the Hardy space there. There's many interesting environments to study Hardy classes, but this is just one. And when we study Hardy classes here on the unit circle, we get something called inner functions, which are quite interesting. So these are given by a theorem by Burling. Someone will know how to say it. Okay. So this is by Burling. And this is about, I think this is chapter 15 of Green-Rudin. Okay. So if I have a closed subspace, and that's not trivial, and E is a closed subspace of H2, it's a stronger condition, and E is simply invariant, then there exists what we call an inner function. So there exists theta. What is theta? And usually I think it's capital theta. Capital theta. And this theta, what is this theta? This is a measurable function. This is actually, well, excuse me. I think this should be an element of H2. Yeah. Sometimes it's measurable, sometimes it's not. Such that the modulus of theta is equal to 1 on T. Oh, exists a, yeah, okay, excuse me. I was getting my wires crossed. Exists a measurable function theta, okay, here, such that theta, the modulus of theta is 1 on T, and theta is in the Hardy class H2. Okay? And the final condition, this is where we get this notion of inner function, E is equal to theta applied to H2. Right, so this is kind of similar, right? We just talked about E being equal to this characteristic function applied to L2. Now we're getting a little bit stronger. Instead of characteristic function, we have this abstract function theta. Okay? And yes. And so the reason that this holds is actually an application of a previous theorem, but the proof of that is much too complicated for this. It's a result by Burling and Helson. But anyway, any function satisfying this property, right? This is what's called an inner function. And as it turns out in H2, we get this factorization of an H2 function into inner and outer functions. So let me see if I can, if there's anything interesting I can discuss there with that, but there may not be. So that's what an inner function is, and that's where they come from. Sort of a natural way of looking at them. That was kind of the crux of this talk. Is because if you read Rudin, if you read Real and Complex Analysis, chapter 15, I think, someone can correct me if they find something else. He talks about inner functions and outer functions for H2, and you're like, okay, well, where did those come from? Well, they come from chapter 17 things. So they come from they come from basically this motivation to study when are subspaces invariant, doubly invariant, simply invariant. Okay, and we know double invariance if we can write that subspace as a characteristic function applied to L2. Okay, but now we're having this existence of a function. We can write E as this function, not necessarily a characteristic function, but we know it's unimodular on T. And so E is going to be equal to that function applied to H2. And as it turns out, you can factor any H2 function as what's called an outer function and an inner function. So this is an inner function. You're going to ask what's an outer function. Okay. Well, remember earlier we were talking about EF being that span of F times Zn. Well, a function is outer. This is why it's so important. If EF is actually just going to be equal to H2. So if EF generates H2, it generates H2. So as it turns out, you can factor any function in H2. So if I have F in H2, okay, I can write F as what notation do I want? We'll say phi. No, that's the bad one. Phi times psi. Okay, here phi is going to be inner, meaning phi is equal to 1 on the torus, and then psi is outer, so E psi. Yeah, we'll just say E psi. That's terrible, isn't it? That's a psi, in case there's any confusion. That's equal to H2. So we have this inner-outer factorization by Smirnov. 1928 is a very old result, but a very good one. Very important one, very useful. So there's what's beautiful about these functions. There's a lot you can do with them. There's many results you can get from them. There's an arithmetic with them. And they have some really nice applications in complex analysis. So this would be some very hard complex analysis. In operator theory, the space of Hardy classes in general is a very interesting space to study, just like L2. Okay, but now we're in the complex plane. We have some more tools as well to talk about H2, which is one of the more interesting spaces to study. But there's other ones. There's the Bergman space, which is you'll see used in several complex variables. There's the Dirichlet space, which is very interesting. But the Hardy space is really, what would you call it? It's just the nice space, the one you always come back to. It's sort of the clutch. But very pretty space. You have some interesting constructions like angular limit, non-tangential limits, some interesting fixed point theorem, some interesting interpolation results. But just as and so this whole talk was just to trick you into thinking I was going to talk about circles, but I really wanted to talk about inner and outer functions because I think that's a rather abstract idea. But I want to show sort of where those come from. And it's actually a very natural construction, inner and outer functions, right? You can see why someone would investigate this. Okay, so, and you can sort of see why you would use the name inner and outer. So anyway, so this concludes the talk. I can give you guys a couple references. Let me just do that right now. So of course, I'd reference the following for stuff on this talk. So for general complex analysis, okay, you're going to be wanting to look at a couple books. So you're going to be wanting to do R and C by Rudin. Okay, and then you want to do Fourier. No, that's harmonic analysis. Excuse me. Harmonic analysis by Katz-Nelson. Very famous Dover book, Katz-Nelson. And then the third one, I should probably just say composition operators by Duren, and McClure operators by Duren. And then specifically for the operator theory side of things, hard operator theory. Let me think here. This would be operators, functions, and systems. And this is by Nikolski. So this book has these all have exercises in them. Obviously, the first one does. These all have exercises in them. I'd encourage you to look through them. I listed these by difficulty, and I'm surprised no one caught it. There should be 4. There should be 4 here, but this is in terms, not really in terms of difficulty. This one's the easiest one. So if you want to get started in this, I'd recommend Harmonic Analysis by Katz-Nelson. And then, you know, the second half of Rudin. Oh, very good, Abdul. Good catch. And then both of these books are quite complicated, but nonetheless, they're readable and they're very good, well written. They're written for the lay audience, both of these. So I hope I've interested you in sort of the field that I work in. You know, if you have any questions, let me know. Feel free to ask or you know, send me a message anytime. I'm always happy to talk about these things. But nevertheless, very beautiful subject, Hardy spaces. You know, comes along with Toeplitz operators, which were big studying the last 40 years. So, and this has some interesting applications. I was talking earlier. So this has applications in filtering and noise, specifically Hardy space methods, and the Riemann zeta function, though I'm not quite interested in that. But yeah, there you go. So just a review. We talked about invariant subspaces. We talked about the characterization of doubly invariant subspaces. And we talked about how doubly invariant subspaces and the characterization of them motivates the factorization of Hardy space functions into inner and outer functions and where those functions come from. And the motivation for studying, the motivation for coming up with this idea of inner and outer. Because you'll notice the definition I gave was rather general, inner and outer. Okay, so this is quite an important thing in complex analysis and operator theory. So anyway, thank you guys all for attending this talk. If you have any questions, I don't know if you guys have any questions, but I'm going to stop the recording here. And